Welcome to the third and last Q&A on incomplete data in the context of the course of longitudinal data analysis. What we will do is, like always, give an overview, a broad overview of the part on incomplete data, with the details, of course, covered in the respective web lectures. So we set the scene by introducing a number of studies like the GROW dataset, and just be reminded that the GROW dataset is actually complete to begin with, but it was used by Little and Rubin to illustrate methodology on missing data by removing some of the measurements at the age of 10 in a sequence of 4 measurements at ages 8, 10, 12, and 14. And that allows to compare, which is something we cannot do usually, what you do when the data are complete with what you do when the data are not complete. So that is the dental data set then, with the depression trial, a genuine data set, a clinical trial where 2 treatment arms are compared for the effect of an experimental drug versus a standard drug in terms of alleviation of depression using the Hamilton score. And what you see here, of course, is that it's a messy bunch of profiles. There are also many, but some of the profiles end prematurely, both on the high end and the low end. And a very important piece of information or even warning is when you see a graph like on the right-hand side with the average evolution, it's actually not the average evolution of the profiles over time, because some profiles are incomplete. So on the left-hand side of the graph, there are more people than on the right-hand side in the case of dropout. So it tells us that if we want to have an idea of what would have happened had everybody stayed in the trial, we need to model first. We cannot just rely on graphical exploration. Very important. Do not trust graphical exploration purely on observed data when the data are incomplete. Then the age-related macular degeneration trial, which was used before, also in the context of non-Gaussian longitudinal data. It's a clinical trial also with 2 arms, with 4 follow-up measurements, and we follow patients, elderly patients, that progressively lose vision. So the outcome in continuous form is the number of letters you can correctly read, but also here there is missingness. And while we looked at graphs or tables like this before, it's good to remind us of what we see here. We see the patterns of missingness. So there is 80% more or less complete, the O standing for observed. There are about 20% of the patients who drop out, and dropout is defined as you're there in the beginning, without any interruption, you're followed over time, and then at a certain point, earlier than planned, you drop out and are not seen anymore. It's kind of a clean process. And then there can also be non-monotone missingness. That is, let's say, you had planned a visit on the day of a strike, but you cannot make it to the clinic. So you are going to miss a visit, but next time you appear again. Intermittent missingness leading to non-monotone patterns. Very important. This is descriptive. So sometimes people deduce, let's say, or speculate what the missing data mechanism might be. But this is not the missing data mechanism. This is just what we observe. The missing data mechanism is the mechanism driving us into a certain pattern. Why do we end up in a certain pattern? Not what it is. So this is a look at the data as it is in a database, whatever format. And you see that there are certain dots or any other missing data symbols depending on the software package that you use. Using an artificial example, we illustrate a few points about missing data. So because it's artificial, it's so abundantly clear that there is a relationship between the actual outcome, let's think of blood pressure in this case, and dropout. Simply said, if dropout or if blood pressure is high, your dropout chance is also high. Good. It's always good to think of, okay, we have a scientific question. Let's not change that scientific question because we have incomplete data. Let's see how we can best answer it. And then, is it in terms of the entire longitudinal profile? For example, what is the slope? Or is it in terms of the last planned measurement? What would be the difference in, let's say, visual acuity or blood pressure at the end of the study? Knowing that not everybody makes it to the end of the study, how are we then going to answer that question? Question mark. Okay, the notation is still the same. We introduce a missing data indicator, R. So for every planned measurement Yij, well, again with Yij, the measurement for patient I at time point j, we have an indicator R, which is 1 if the measurement is taken and 0 otherwise. Of course, sorry, if you have dropout, you don't need an indicator for each and every measurement. You just count the number of measurements that you have. For example, if we go back to the ARMD study here, we can say we call the completers pattern 5 and then the dropouts respectively 4, 3, 2, 1. So then we have number 10. But of course, that doesn't allow us to effectively describe the non-monotone missingness. So if there is non-monotone missingness, we need the R vector. That's an entire vector of indicators. But if it's only dropout, a simple number will suffice to describe the pattern. Okay, this is a bit premature, but it tells us where we are going. And of course, if you've watched the web lectures, it will make sense. The bottom line is the following. Whereas in theory, you have to build a model for the outcome, blood pressure, and the dropout indicators together, in a very specific case where you use maximum likelihood or Bayesian estimation, there is no need to model the missing data mechanism. It's sufficient to model the observed outcomes. This makes our life quite a bit easier, at the condition that the mechanism is missing at random. So we're using likelihood, the mechanism is missing at random, and a few regularity conditions hold. In particular, that the parameters describing the outcome Y and the theta and the parameters describing the missingness process R are distinct of each other. That's usually a fairly trivial condition. So in that case, we can ignore the missing data mechanism. And this is important for us and for many other courses or techniques that we use, because we've seen the linear mixed model, the generalized linear mixed model. There is also the nonlinear mixed model. They are likelihood, they're estimated with maximum likelihood or Bayesian fashion. So these methods remain valid as they are, just as is, even though the data may be incomplete. And that's the first very important technique that we put forward, one of many, when we have incomplete data. So still to this day, I mean, it's well understood, but still to this day, there is often a bit of confusion. People think they have to do all sorts of things when the data are incomplete, filling them in, deleting subjects, etc. No. What we are saying here is just analyze the data as they are. If somebody in the ARMD study has 4 measurements, fine, because that's what we planned. But if they have only 1, 2, or 3 measurements, we can also use them. We don't need to do any processing before we fit the mixed model. It took a while, and I will skip over that right now for it to catch on, especially in the context of clinical trials, and that's because it's such a heavily regulated area. So there can be the scientific insight that direct likelihood is good and works, and now we're talking about the 1970s, 1980s of the previous century. But if the Food and Drug Administration then says, no, we don't want that technique, it's of course hard in a clinical trial to switch to that method, and that's why less good techniques stayed on board for quite a while. Also, still to this day, there is some confusion in the literature. There is the term informative missingness, which is actually not necessary. And missing at random and ignorability are often confused with each other, but that's not entirely correct, etc. Dropping out you can do from the study, which means no information whatsoever. You're planned to be in the study for a year, but after half a year you give up, and yeah, then there's no information on you whatsoever. But you can also drop out from treatment because the physician thinks that you should get rescue medication. They may keep you in the study to follow you up, but not any longer under the experimental treatment for safety reasons. And then, of course, the information is becoming different. It's not what we plan to do, but you're still followed up, etc. So we have to be very precise in our terminology. And then briefly, over the years, we've reached a point where the academics, the industry, the regulatory authorities, and very important also patient representatives kind of joined forces to come up with a wholesome framework. And that's where we are now, also based on the National Academy of Sciences experience, which I explained in some detail in the web lectures, where now I think we have good consensus on three important parts: terminology, how the definitions, how do we talk about missing data? That's the first thing. Let's agree on a language before we start using it. Then we should not forget prevention is better than cure. So every data point that you can collect is better than having to deal with missing data, of course. But for many reasons, including the Convention of Helsinki, you cannot force people to respond, which is why, of course, we need to deal with missing data nevertheless, and that's the treatment side. Slide 548 is very important because it's a good, simple summary of the terminology that we use. We in this course and also in the report from the National Academy of Sciences, the prevention and treatment of missing data in clinical trials. So there's the pattern. There are 5 dimensions in blue, and then the first one with the red dropout pattern is applied to the specific case of dropout as well. So, but in general, whether it's a longitudinal study or a survey or an epidemiological study, anything else, we distinguish between complete, monotone, and non-monotone patterns. But of course, in the case of time ordering, like in longitudinal studies, we can talk about dropout and intermittent missingness because that reflects the time ordering. And we drop out at a certain point in time, or we miss a visit, but later we come there again. You see that there is reference to time in the way I describe it. Then there is the model framework. You, as a modeler, decide what model you are going to use, what model framework. That's a choice of the statistician, or actually the scientists. The mechanism, that's not our choice. That is the mechanism shooting holes in the data set, making or actually driving for every measurement, for every subject, the probability of being observed or not. And of course, we will talk about those. Then ignorability has to do with how valid is our inference if we do not use the missing data mechanism. And when we say, I already did that, when we say inference, we can do that in 3 major ways: likelihood-based, Bayesian, but of course also frequentist. And have we seen frequentist techniques in this course? Yes, a very important one. Generalized estimating equations is not likelihood-based. We deviate from it. We use an estimating equation for the first moments, the mean function. We kind of correct for the correlation and we leave it at that. That's not a full likelihood specification, and therefore it's also not a Bayesian technique. So it needs special attention. Okay, the NAS panel, as it was, I was part of it, but other than that, that's not something we have to spend too much time on. But this one, yes, 550 is also a very important slide because it contains 2 of the dimensions. So In general, we need to model Y and R, and you know what I mean by Y and R in the meantime. Y is the outcome of interest, blood pressure, or the Hamilton Depression Score, or the body length, or whatever measurement we are following over time. R is the corresponding set of missingness indicators, and of course there are covariates: treatment time, treatment by time interaction, age, sex of the patient, etc. Okay, that's a joint model for Y and R, and we can break it up into two different ways. Many, but two important ways. In a selection model, we have a model for Y and a model for R given Y. In a pattern mixture model, it's the other way around. We have a model for Y given R and a model for R. And then in a shared parameter model, we bind Y and R together. We connect them by a latent variable that is common to both. And I use the notation of a random effect because it actually is a random effect. But because the random effect is shared between the two model factors, we call it typically a shared parameter. Okay. If ever you get the question, is a selection model right or a pattern mixture model right? That's not the right question. Why? Because the selection model and the pattern mixture model, as I write it down in probability theory terms, is nothing but a factorization of the joint distribution. It's the law of total probability. If I have a model for A and B, then I can split it in a model for A and a model for B given A, or the other way around. And that's what we are doing here. So the question is not so much right and wrong. The question is, which of the frameworks allows me to answer my research question best? If I want to estimate the treatment effect overall, a selection model is the right thing to do, because in a selection model, I have the model for Y that I would have even in the case of complete data. In a pattern mixture model, you could answer a question like, among those people who stay in the study, is the treatment effect better than those who drop out? Well, then of course, I want to look at Y, given that you are complete, and Y, given that you are incomplete. And of course, because that conditioning is intrinsic in the first factor, that's a pattern mixture question. Sometimes it happens that in the same study, we have questions of both types. So the patterns, we have already made some progress. The patterns is something that describes what the data look like. It's a descriptive tool, the patterns. The model framework is something that you and I choose according to our research interests. And then we have the missing data mechanisms, and they're most easily explained in terms of selection models. So the factor in a box, that is the missing data mechanism. And of course, you see that in general, it can depend on X, the covariates, on the observed outcomes and the missing outcomes. But in the specific case that it does not depend on the outcomes, we talk about missing completely at random. When it depends on the covariates and the outcomes, but only the observed outcomes, we talk about missing at random. Now, don't look too much into the names. The names are fairly useless. We could call it type 1, type 2, type 3. That would be easier because people start to say, okay, missing at random, it means everybody has the same probability of missingness at every time. Wrong. That's not true. Randomness doesn't mean equal probability. So it's actually not really about randomness. It has to do with relationships between variables. So what missing at random says, given the covariates and the observed outcomes, there is no further information in the missing outcomes. And that's of course very nice, because it means that you can model missingness in terms of things that you have observed. Easier to model. Whereas under missing not at random, you further have a dependence on what is unobserved. We hope that this is not the case, but we can never exclude it. So one important message also present in the book and in the web lecture is we cannot distinguish based on data between missing at random and missing not at random, whatever you read about it. And the reason is simple. What is the difference between missing at random and missing not at random? The missing measurements, but you don't have them. So to test whether missing at random and missing not at random is more plausible, you would need the missing values, but then they're not missing values. You don't have them. It's not possible. So that's why we do sensitivity analysis. We're not going to complain about it. We're not going to agonize about it. We will do sensitivity analysis. So we can actually distinguish between missing completely at random and missing at random. There are tests for that, and that's okay, because the difference between those two is the observed outcomes, and you have them. Only, I think in most cases, it's not so useful to do, because techniques under missing at random are simple to apply. 1. 2, whatever is valid under missing at random is also valid under missing completely at random. Don't make a mistake there. Sometimes we see that happen. People say, well, it looks like the data are missing completely at random, so therefore I cannot use a technique for missing at random. No. A technique valid for a higher mechanism is also automatically valid for the lower mechanism. In particular, anything that applies to missing at random also applies to missing completely at random. Consider missing completely at random a special case of missing at random. That's a better way to think about it. Okay, so here is the same information, but then already with techniques added to it. And now I can give a simple overview of techniques, and then in a way we have covered everything in the part on missing data. That is, we usually start analyzing the data from the assumption of missing at random. And then we have a direct likelihood approach, a direct Bayesian approach. I already mentioned that. We also have multiple imputation and weighted estimating equations. And these are the techniques that we develop in the rest of the part on missing data, which means that techniques only valid under missing completely at random or other simple methods like complete case analysis, last observation carried forward, single imputation methods, we don't use typically. That's, I think, the message. Of course, as I just said, we cannot exclude missing not at random, and that's why we do also sensitivity analysis. So we start here, and then we do a sensitivity analysis, and there are a number of techniques. I briefly illustrate that at the end of the part. The good news is that sensitivity analysis nowadays can be done quite easily, actually, using SAS software, PROC-MI, in the context of multiple imputation. So that's actually a summary in the middle of the part, but which also is repeated at the very end of the part on missing data. It says it all. It's basically repeating what I just said. We start in the middle under missing at random. We have direct likelihood, direct Bayes, weighted GE, multiple imputation. They're easy to conduct for Gaussian and non-Gaussian outcomes, and we can use standard software for it. Missing completely at random, forget about it. I mean techniques only valid there. I actually mean techniques like complete case analysis, last observation carried forward, other imputation techniques, forget about it. But when you started with MAR, don't forget to complete it with missing not at random. Okay, I will be brief about it, but what we actually say here in this 30.20 is you always make untestable assumptions with missing data. Your models almost always say something about what the missing data would have been, and that's something to be very aware of in a case like that. The illustration in 30.21 tries to do two things. First of all, indicate how unrealistic LOCF and CC is. So you have, it's not a real data set. It's a simple 2x2 table with one supplemental margin. Under LOCF, you basically say, okay, if you say yes the first time and the second time you don't show up, and there are 75 people like that, we keep them in yes. So they become yes, yes. And the 25 others become no, no. What it basically says is under the LOCF assumption, if you drop out, you cannot change opinion anymore. Nothing can change, and that's of course not realistic. You see that because you have a very bizarre table then in this case. CC says, okay, if you're incomplete, we're not using you, but you throw away information, of course, which is not the cleverest thing to do. So therefore, you even see that in this case, you have very different estimates of the proportion of people who say yes twice. It's almost the half of it under LOCF. It's only 20% with CC. Whereas missing at random, and it's in detail in the web lectures, but I will explain it here also, because this gives us a good idea, good intuition of how MAR works. We say, okay, we have 75 people who say yes. That information we will not touch. But how would they split over yes, yes, and yes, no? We have information on that also, because they are split among those people who have the second measurement in proportions 0.40 and 0.60, 40% and 60%. So we will apply the same split to the 75, and that will give us 30 and 45. Same story for those 25. We split them according to 0.20, 0.80. So the numbers 5 and then the number 20 appear. Is that the correct way of doing it? That is what happens under missing at random, and everything that deviates from it slightly or more becomes a sensitivity analysis. Do we do it like this in practice? No, as I said, this is a simple way where we can indicate what MAR actually does to your data. It uses the information that's available, the observed data, and then it uses the predictive distribution from whatever else you can find in the data set. You don't have to do it by hand in this way. In practice, if you fit a linear mixed model using maximum likelihood on incomplete data, at the more complex level, this is what the likelihood automatically does, and you do not need to do anything specific for that. It happens automatically, fortunately. So that points to the proper analysis of incomplete data. In the first part of this section 31.11, I indicate what the various techniques would do on the artificial data set. So complete case analysis only uses the bottom group. An available case analysis, which is, okay, you calculate the average of whatever is available, gives a very strange profile. Because it takes a proper average until the middle and then it drops down, which of course is an artifact of dropout, not of what's happening with blood pressure in the population. LOCF would carry forward the incomplete patterns, and even though everything is increasing over time, you ignore that and the LOCF prediction would be flat. Whereas under MAR, you would have actually a prediction that is still sloping upward. That happens again automatically, and that in this case would be a better thing to do. So complete case analysis is, well, that's actually a bit of a complicated thing for many people. It's valid under missing completely at random. Now, a common misunderstanding is, therefore, I have to use CC under missing completely at random. No, no, no. It's not because a method is valid that you should use it. Let's say I want to determine the location parameter of a simple single normal sample, mu. How can I do that? With the mean and the median. They're both valid, but it's up to you to choose one or the other, maybe even another estimator according to what you consider important advantages and disadvantages. The problem with a complete case analysis is it's wasteful with information. It's inefficient. And missing completely at random is not very plausible in the first place. But so last observation carried forward, not even valid under missing completely at random, so usually biased. Okay, we try to illustrate that in some detail here, but it's good to say, okay, let's now put to rest these methods and look at ignorability. And we go through the motions and we actually show that if you choose for maximum likelihood and you have missing at random, then the actual the likelihood is to be in terms of what you observe, which is the observed outcomes, of course, the covariates X, but they are not part of the notation, but they're there. They're there. We allow for covariates, and then dropout, D or R, it doesn't matter. The thing is that in general, you need to integrate over the missing data components. But under MAR, the missing data components are not present in the second factor. You integrate over ym, but the second factor is free of ym. You therefore can put it up front, and your likelihood effectively factorizes into two factors, which means the log likelihood factors into two terms. The first one depends on theta only, the second one depends on psi only, and you can estimate them separately. Now, okay, you can estimate them separately, but if I'm interested in theta only, I can use the first factor of the likelihood, so the first term of the log likelihood, and forget about the second one, ignore it, because I can use it, but I don't have to if I'm not interested in it, and that's where ignorability comes from. So, under very broad conditions, likelihood and base is valid under MAR as is, without additional work. Sometimes we get a bit nervous because we think that, okay, the data are incomplete, we should do something extra. No, not true with likelihood and base, because the theory says it, and the theory is even relatively simple. But of course, it doesn't cover frequentist methods. And what frequentist methods do you know? Many. I'm just randomly naming a few. Cochran, Mantel, Hensel, Fisher's Exact, Mann-Whitney. I can go on like that a little bit, but at the modeling framework, GEE, Generalized Estimating Equations. By the way, also many other smoothing, spline methods, etc. So in that case, only missing completely at random guarantees ignorability. Very important remark. There are frequentist methods or non-likelihood methods that are valid under missing at random. These are exceptions, lucky exceptions. So that's not the general result, but I'll give you one example that I also mentioned in the web lecture, REML, restricted maximum likelihood. It's close to maximum likelihood, but it's a little different. We even discussed it quite a bit in the presentations of the first assignment. So it is not likelihood, but it's a very close brother or sister of maximum likelihood, so close that we can actually show that also REML is ignorable under MAR. It's a good counter example to the general statement. But can we say that for GE, for example? No. For GE, under missing at random, in many cases, it would not be valid. We need to do something extra. That's the slide that I have already shown. Very nice for direct likelihood. There are a few illustrations here that I would like to point to. So what we do is we analyze the original orthodontic row data set, and just know that the original orthodontic row data set is complete. So there's no problem at all. It's a nice balanced data set. We go through the motions and we find a very nice simple model, a linear mean for boys, a linear mean for girls with a different slope, and a simple variance covariance structure, a very simple multivariate model. Okay. If we look at the trim data set, sometimes we say the 1987 version, we see that whatever simple method we use, it goes all over the place. So forget about it. 569 is a set of techniques we should not use. If we use direct likelihood, though, we still get the same model as before. But a very important observation is, if you look at the bottom right panel, but also the top left panel, we see that there are actually three things here plotted. There is the big diamond, there is the small diamond, and there is the point on the line. That explains how MAR works with likelihood and that it works. The big diamond is the mean of the, in the case of boys, 7 boys still observed in the 1987 version. The small diamond, actually the small, I should talk about the girls. So the big diamond is the 7 girls that are still observed in 1987, whereas the small diamond is that of the 11 girls that were there originally. So what you see is that the mean of the remaining girls is higher than the mean of the girls that were there from the beginning. So the ones that have been removed from the data set are smaller, and the likelihood knows that it corrects downward. A bit too much, but that has to do, that's not a bias thing. That has to do with variability, because after all, this is a very small data set. That's the reason why. So why the likelihood is not simply using means. Yeah, that's what it does when data are complete and balanced. 2 slides ago, that's exactly what it did. But now it's actually using also predictions. So for the girls that are, and the same for boys, that are not observed at the age of 10, it uses the prediction based on the information that we do have for these children, namely for the previous and the next measurements at the ages of 8 and 12, and the likelihood uses everything, also the one at 14. And of course, if you think about it, that's logical, because if we look at growth, if I have the previous measurement and the following measurement, I have a pretty good idea about your body length. So intuitively averaging those would give me a good prediction. It's not a population mean, no, it's your prediction, and that's what the likelihood is using in general. Okay, we then illustrate this a bit further, but I'll be brief about it, with the same data set, focusing on the first and the second measurement, the first complete, the second one partially missing. And what you see is that the number of techniques that we have known for a long time, likelihood with ML, with REML, MANOVA, ANOVA per time point, that's all the same up to small differences in the standard error when I have complete data. Complete balanced data. Now that balance is also present with complete case analysis and with LOCF. Yeah, I've made it this way. With complete case analysis, I've restored the balance by throwing away information. Not a good thing to do, but what is left is balanced. LOCF, I fill in the missing value, so that creates balance again, but in a very bad way. And then the 4 techniques rather, are still all the same, but different from what they should be. And this is it now. Whereas ANOVA and MANOVA do the same thing in terms of means for balanced data, they do not for unbalanced data. And in particular, they don't do that for incomplete data, because incomplete data are also unbalanced, of course. So that is because ANOVA and MANOVA simply calculates the mean of what happens to be available. And likelihood is much more clever than that. It says, okay, I will use the data points that are available, and I use the best predictions for the data points that are not available at a given point in time, and we get a better result in this way. So this is explained in detail. It's the same thing now, but then to show it in formulas in a simple example. Remember, I gave the 2x2 table with a margin to give a simple illustration. The other example I can think of is a bivariate normal, where I also can illustrate methodology quite simply. And why is that? Well, if you have a bivariate normal, any conditional, any marginal is also normal. And this is the predictive distribution of the second measurement given the first. So if the second measurement is unavailable, but you have the first, you can come up with the best possible prediction. Importantly, also, you have an idea about the prediction uncertainty. That will be very handy when we go to multiple imputation. But now you see that actually this prediction is used in the likelihood expressions for the mean, in the explicit forms for the maximum likelihood estimator of the second mean. Whereas in a frequentist fashion, you would say, okay, I plan 16 boys, I only have 11, it will be the mean over 11. Biased because the sample is biased because of missingness. Okay, now I just mentioned the variability. The variability, of course, is important. The way I actually, the variability in the data, which is also, of course, dependent on sigma 12, the covariance. Because if there is no covariance, there is no correlation, then Y1 and Y2 are independent. It's thanks to the correlation. Think of the growth measurement. My body length today and my body length tomorrow, they're not independent. What would that mean? That I shrink and expand all the time? No. It's pretty much going to be correlation, almost one, if we talk about body length. Other quantities are a bit weaker correlated, but it's the correlation that allows me to come up with a subject-specific prediction. Of course, if I mismodel my data and I say, okay, I will use independence as a correlation matrix, then I set the correlation equal to 0, and you see what happens. Then I get, in the incomplete case, actually the same thing as I would get with a complete case analysis. Because for the prediction to work, the correlation structure needs to be correctly specified. Not for balanced data, because with balanced data, there is no correlation to be found in the forms of the estimates. But if the data are incomplete, the predictive term is added to it, and that predictive term contains a regression coefficient, and that regression coefficient depends on sigma 1, 2. The bottom line, and I'm saying the same thing again, sigma 1, 2 should be correctly modeled. If you wish, that's a bit of a downside, or rather a condition for the likelihood to be ignorable in a proper way. Everything needs to be correctly modeled, not just the mean structure, also the variance covariance structure. Okay, and that's the same thing graphically. Then we indicate what you should do in terms of software code, and that is nothing. The code that works in the complete situation, it also works with the incomplete situation. The one thing is you have to tell exactly what measurements are what. So if the software for some reason would think that for subject 3 you have the first, the second, and the third measurement, no. It's the first, the third, and the fourth. That's why I usually advise not to organize the data set in this way, but to add also a record for the missing measurement, which would be 3, 10, 2, and then a missing value. Don't fill it in. Fill in the missing value symbol as it properly should be, but that way you tell the software explicitly that there is a first, a second, a third, and a fourth measurement, and the second happens to be incomplete. Of course, by improp mixed adding the repeated age, we also take that into account. That repeated effect needs to be a categorical variable, so in case age, it should be modeled in the mean as linear, as continuous. Then you create a second copy of age, one a class variable, the other one not a class variable. Okay, let's look at the depression trial and see how they differ from each other. Very briefly, what we see is that we have under CC and LOCF non-significant results, under MAR, so direct likelihood, barely significant. It's at a different side of the 5% line, and of course I would not say this is highly significant, of course not, that's not the case. I would even doubt a little bit whether this is really stable, yes or no, but that's why we will have to do sensitivity analysis, of course. We can analyze the ARMD trial in its continuous version with a full multivariate model with 4 treatment effects, 1 for every time point. We can do GE and GLMM, but wait a minute, for GE we are not ready yet because we have not discussed weighted estimating equations, but GLMM is also a likelihood-based approach, so that can also be applied. By the way, the likelihood-based approaches, it sounds in this course, they're all mixed models, but of course not. There are many likelihoods that we can use in many contexts that are not using random effects. The most important thing is that you use maximum likelihood and that you assume MAR. Okay, there's a bit of bookkeeping here, macros that you can use for CC and LOCF. Let me repeat, it's not because we make these macros available that we suddenly think it's a good method. I think I've made it clear that CC and LOCF is not something that I would like to use, of course. But again, if you look at this program for the linear mixed model, so for the direct likelihood analysis, There is nothing specific for the case of missing data. This is the code that I would use if the data were complete, and this is the code that I use when the data happen to be incomplete. Okay, for GE, we will do that later. For GLMM, same story, the same code as we would use otherwise. Proc-ML mixed, same story. Okay, we always like to compare a little bit the good method, direct likelihood, with the poor method, CC and LOCF. And does it matter? Yes, it does, because we see, for example, that and I'll just single that out, at 52 weeks, we have a significant treatment effect with direct likelihood, and now it's a bit stronger than in the depression trial, but not at all with CC and LOCF. And this is important, because as I explain in the web lecture, the treatment effect is actually going the wrong direction. The vision is worse in the active group than in the placebo group. And that is because the liquid that is injected in the eye is viscose. It's very syrupy. And therefore, people with the active treatment, they have a blur in the eye that actually lasts for a very long time. So therefore, we better know this, so that we can take precautions. With CC and LOCF, it doesn't look as bad as it should be. So that's a warning that a proper analysis is what you should do, and not say, okay, CC and LOCF, they're usually kind of okay. No, they are not. All right. This is same story then for the binary outcome with the mixed model, with PQL, which we know doesn't work very well, and we see that here once again, and with numerical integration. Because of the binary nature of the outcome, we see very little effect, of course. Now, weighted estimating equations, I will go over it very briefly, just give the intuition again. Weighted estimating equations, what they do is they use a different principle than direct likelihood or direct Bayes. What is the principle on which rests direct likelihood? The use of the predictive distribution. The distribution of what you don't have given what you have. Why miss given why ops and covariates. That's the predictive distribution. That's how the correction works. There's another corrective mechanism that is for those people who took sampling theory once, they know that, using weights. To put it simple, if I'm in the data set and my probability for dropping out is 50%, that means for people like me, 50% are observed, 50% are unobserved. So my data get weight 2, because I compensate for the 50% that are not there. If my probability of being observed is only 10%, it means that for every 10 people like me, on average, only 1 is observed. So I have to compensate for 9 other people. We are 10, not just me, so I get weight 10. The smaller the probability of being observed, the higher the weight. Inverse probability weighting, 10% becomes weight 10, 50% becomes weight 2. 33.333% becomes weight 3, etc. So that's where it comes from. And that's what I wanted to repeat about weighted estimating equations. There are, of course, subtle ways of doing it in practice, but that's the principle. I can do that for the entire subject at once. And then I ask the question, what is the probability for a given completer to indeed be complete? Again, if that's 50%, weight 2, if that's 10%, weight 10, etc. But I can also do that slightly more subtly, and that is at the level of the individual measurement within a subject, because the probability of the first one to be observed and the probability of the last one to be observed may be very different. So a later version of weighted estimating equations doesn't simply apply the weight to an entire sequence, but rather to every measurement within the sequence. And that's actually, in a nutshell, it's not a theory, but it's the intuition behind the theory. Okay, so once you have probabilities, you invert them and put them into the estimating equations. And in the web lectures, I give some details on how you do that step by step indeed. Okay, let's apply to the analgesic trial, where we have where we see that we have a lot of missingness. These are cancer patients with pain, serious pain, unfortunately. So what we try and do here is alleviate their pain. But you see where you start with 530 patients at recruitment. At the final time, only 223 are left, 40% less than half. And we see that very clearly in the patterns. It's more severe than in the ARMD dataset, in the ophthalmology dataset. Only 40% completers, another 40% more or less drop out, and then you still have 20% of intermittent missingness. A downside of weighted estimating equations is not easy to use with non-monotone missingness. That's one downside. Another downside is using weights may help you correct bias, but it reduces precision. It makes standard errors larger. It makes confidence intervals wider. So it actually tells us that weighted estimating equations, yes, can be used, but it's not a miracle tool, which is why we would revert at one point to something like multiple imputation, the last technique that we will consider in this part after this one. So let's apply it to a few cases. I'll discuss one, and then there are more, and the analgesic trial. So because you first have to build a model for the weight, we start with the logistic regression, not a final model yet. It's a help model, an auxiliary model. What is the probability of dropping out now, given that I'm still in the study, and given my previous pain score, given my pain control assessment at baseline, my physical functioning, and my genetic disorder or my genetic dysfunctioning. So here are the parameters of that model, not of interest per se, but we can use that to build into the weights. So the final model is going to be very simple. We say the probability of having a favorable outcome, because we model the data in a binary fashion, depends on the time point at which I'm looking and pain control assessment at baseline. But the point I make here, and it's more dramatic than in the other examples, is all of the effects are significant with GE. None of the effects are significant with weighted GE for two reasons. In this example, the point estimates are all corrected downwards towards zero. So the GE estimates are overestimated. And that may go in one direction, and in another example, it might go in another direction. Perhaps even for different parameters, it goes up, and for other parameters, it goes down. But what is almost always the case is with weighted GE, the standard error goes up. So if the point estimate goes down and the standard error goes up, you know what might happen, and what's happening here in all effects, significance becomes non-significance. But it actually tells us that GE may come up with spurious, incorrect, significant results. So we may read too much into the data. But of course, it also has to do with the inefficiency of weighted generalized estimating equations. Okay. In the old days, and I must emphasize what I show here on 599 and 560, we don't do anymore these days. We had to do a logistic regression for the weights, and then GenMod with repeated, so GE for the final analysis. Nowadays, we have the very useful prop GEE in SAS, where apart from a single amount of bookkeeping, everything is done into one procedure. So that one procedure has a model statement for the final model and a mismodel statement for the dropout model. Very convenient. Okay, we do the same thing for the ARMD trial, but here let's go straight to the result. And here we see very clearly the impact of weighted GE. If you look at basic GE and weighted GE, again, the point estimates are different. Now they went up in many cases in weighted GE, but look at the naive versus the robust standard error. If you look in standard GE, in this case, robust and naive are almost the same, but not with weighted GE. Why? You do see the impact in the robust standard error of the correction. The weights really are shown up in not so nice a way for us in the robust standard errors. That's for the linearization-based method, same thing. Yeah, the code we have discussed once and for all. The ARMD trial now, but with ProcGE. And here I'm going to look at what I said before. The subject level weight, it's all weighted estimating equations here, but in two different ways. And what I said in the beginning is you can apply the weight at the level of the entire subject. So you take you build a model for the weights, and then you look at a completer and you say, what is the probability for this person to be observed? If it's 25%, the weight becomes 4. But at the observation level, you do that observation by observation. First of all, you don't have to analyze at the end of the day the completers only. Second, you can differentiate the weights between the first, the second, the third measurement, etc. And you do see the impact. Observation level weights, they came later. They were, let's say, an improvement. They require a bit more computation, but the software does do that for us, so that's okay. And you see that the standard errors are more favorable in the observation level case than in the subject level case. Fortunately, you can do both in SAS ProcGE. Even more fortunately, it's even the default, the observation level weights. So that's what I'm summarizing here, and that's also what I recommend. Okay, that's again a bit of the code. I'll skip over the code right now. Finally, we look at the depression trial, and again, we look at the results only. And this is a case where actually the correction seems to go a different way. Weighted GE gives for the last visit a significant treatment effect. Standard GE does not. But didn't we say that the standard error goes up? Yeah, and it does, but very little, from 38 to 39. It's an increase, but a very small one. But the correction of the point estimate goes from 71 to 84. So that can go both ways, as I've said a few times. It goes in the way of a larger effect with an only very little increase in the standard error, and on the balance we see a significant p-value. So that's of course also possible. Anyway, there are a few disadvantages to weighted estimating equations. I mentioned two. The precision is not great. It's limited to dropout. So even if you have a little bit of intermittent missingness, you have to do something ad hoc with it. And you do all this work and there is still the problem with intermittent missingness. Further, weighted GE is weighted GE. It's a correction for one technique. Multiple imputation is a token technique, one that you can apply in really many settings, and one that we put forward as a very favorable technique to use, very useful. I'll explain the general idea, but I already referred to it earlier. When we were discussing, remember, direct likelihood, I gave an example with a bivariate normal, and I said, well, the conditional distribution of the second measurement given the first one is still normal with a predictive mean, and importantly also a predictive variance. That predictive variance is what we are going to use now also in multiple imputation, because if you have a predictive distribution, yeah, that predictive mean is used in direct likelihood, but we can do something else with the predictive distribution. We can draw from it because it's a full distribution. We can draw from that distribution, and if we draw from it multiple times, yeah, if you have a distribution and you sample from it 1,000,000 times and you plot a histogram, you recover the distribution. 1,000,000 times is a bit too many. We usually take small numbers, 10, 20 per data point. So here we go. Every data point is replaced multiple times by a draw from that distribution. We will discuss the times a little bit. So that's the idea. We construct a predictive distribution, we draw from it using software. But then, of course, your single incomplete data set, and I can rather show it here on this graph. So your observed data are incomplete. You impute perhaps 5 times, 10 times, 20 times, and you have 5 on this graph completed data sets. They can be analyzed with the same techniques that you would have in mind, any technique that you would have in mind had the data been complete. Easy. But then, of course, you have not a single result, you have 5 results. There are combination rules to turn that into a single result, indeed. There's a bit of a justification that we go over and how it actually works in practice with some subtleties. And then finally, the combination rules that I mentioned. For parameter estimates, that is nothing but averaging. If I have estimated my treatment effect 20 times, is the average of those 20 treatment effects. For the variability, there is within imputation and between imputation variability. Those people following optimization and numerical methods will have seen it there as well. So the within variability is the variability that you would have even if the data set been complete. A way to think about it, that's because we have a finite sample out of a much larger population or perhaps even an infinite population. And the between variability is actually the additional variability that comes from the fact that your data are incomplete. The information that you are missing increases the uncertainty, and that's captured by the between variability from one imputation to the next. Okay, you can also do hypothesis testing, and all of that has been built in the R functions for it. And there is the mice package. There is also proc.mi in SAS, proc.mi analyze, where all of this can be done as well. So in practice, let me explain it in SAS terms. Proc.mi is the first step to generate the imputations. Once you have those, proc.my favorite, and that's not a procedure that exists, that is whatever you have in mind. Proc univariate, proc t-test, proc rec, proc GLM, proc genmod, proc mixed, whatever is used, and then those results are combined into a single result using proc.mi analyze. Okay, if we apply the multiple imputation technique very briefly on the orthodontic growth data set, we have the original data set and we can then analyze the incomplete data set with multiple imputation, and we get a result that's a little too small, but we already saw that with direct likelihood as well, so it's the same technique. But a bit more interesting is the ARMD trial. We're going to generate 10 imputations. It's 10 or 20 is a fairly commonly used number. And then once that's done, we can use GE and we can use GLMM. Another advantage of proc.mi is, I'm going to analyze the binary outcome, loss of lines of vision, yes or no. But the underlying variable is visual acuity. So what I can do is do the imputation at the level of visual acuity, and only after the imputation I dichotomize. So I use a much richer imputation model than what I'm finally going to use for analysis. Okay, should I do it for GLMM? Strictly speaking, no, because GLMM is a technique, likelihood-based, where I can use direct likelihood, and then I don't even need multiple imputation. But GE, yeah, that's a frequentist method for which you can use weighted GE, but we discussed the disadvantages, so we use multiple imputation instead. And if we do multiple imputation for GE, we might use the same imputed databases for GLMM so that we can make a direct comparison between the two columns. And that's what's happening here. Okay, in SAS and in R, you have many tuning parameters. So you need to familiarize yourself with the tuning parameters. But there are 3 broad families. Monotone. That is a technique that can be applied only when the input data are monotone. So there is no intermittent missingness. then it's fast and simple, but that's not always the case. No panic. Oops, sorry. We also have MCMC. MCMC works with any type of missingness. So we built a big multivariate model for my vector of outcomes, and I draw from that. A full multivariate model, but that may sometimes be a bit complex, and especially when you have some outcomes continuous in the same data set, and some outcomes continuous, some binary, some categorical, some count, some time to event. Yeah, what multivariate model should I consider for that? That's not easy. So that's why we also have full conditional specification. What it essentially does is we cycle through all the outcomes. So we have, let's say, there are illustrations further down, but you have, for example, a vector of outcomes like in the R&D data set. You build a model for the second outcome given the first, the third outcome given the first and the second, the fourth given the first, the second, and the third, etc. This has the advantage that it's simpler in case where the different outcomes are of different types. Because you model every outcome separately given the others, you can use the proper model at Poisson for counts, logistic regression for binary, etc. And it works for non-monotone missingness as well. Okay. Here is some code. You know that I don't focus too much on the code, but I will say a few things about it anyway. ProcMI does the hard work, but for you as a programmer, the code is very simple to use. You specify the variables for which you want imputation, and very importantly, that should also include variables that are complete. So lesion, the type of lesion in the eye, treatment is complete, yet I need to correct for it because any variable that I'm going to use for analysis later should be present in the imputation stage, whether complete or incomplete. The seed allows me to fix my imputations. That means if I run this program and I generate my imputations and I give you the same program in the same data set, you will get exactly the same imputations. If there is no seed, it will use the actual clock of your computer, and every time the seed is a bit different, and you can never repeat the analysis in the exact same way. So that's a precaution in case that the analysis should be reproducible and repeatable. Rounding, yeah, maybe we don't want the number of letters read to 16 decimal places, so maybe 1 is fine, 7.3. Don't round it too much. You will say the number of letters you can read is a count, true, but it's actually better for the imputation to have a certain level of refinement. So 1 or 2 digits is not a bad thing to do. Okay, and this is then the same idea for ProcMI, but now with full conditional specification, where you see I do specify my regression and say at week 4, there is a dependence on lesion and treatment, because it's by treatment. At week 12, there is a dependence on lesion and the previous outcome, etc. So that's a very logical thing to do. And then I dichotomize my outcome, I do a bit of transformation. We will not dwell too much on the software details, and then I analyze my data. So very important, if I do, for example, GE, I should do that by imputation, so that each of the 10 or 20 or 30 imputations is analyzed separately. And with the ODS statement, I make certain that the output that is relevant, so parameter estimates and variance covariance matrices, are preserved. Same story for GLMM with ProcNL mixed. And for those of you who want to use ProgLi mixed, perfectly fine as well. And then I do the inference task. Again, relatively easy to use. The model effects is all the parameters for which I want to have this combined inference at the end of the day. It doesn't need to be everything. If you say, hey, wait a minute, the intercepts and the treatment effects at earlier times, I don't care. Well, then you may write model effects, treatment time 4, and that's all. That's entirely your choice, of course. Okay, that's it. That's how it works. What you can also do with ProcMI is create monotone missingness. So that's not imputing everything multiple times. It's only the intermittent missing values that are imputed. Why is that useful? I can think of two uses. If you insist on using weighted estimating equations, I just said weighted estimating equations cannot use intermittent missing profiles. Well, in that case, what I can do is use PROC-MI to make the general missingness into the simpler monotone missingness and then use weighted GE. I illustrate that a bit further down. Would I do that in practice? No, I don't think I would do it. I would actually prefer multiple imputation period. But another use where it's very useful is in sensitivity analysis. Some sensitivity techniques only work with dropout, not with intermittent missingness. So then I can use PROC-MI under MAR, so PROC-MI under MAR to make it monotone, and then apply my sensitivity analysis to examine the effect of non-monotone dropout indeed. Okay, that's what I wanted to say about this. Then I apply that to the estimating equations, but let me straight go to the results. Very important, this is not your regular use of MI, because I see here standard G without MI and after MI. It's still not valid because this MI is not a full MI, it's only MI applied to the intermittently missing values. So the top panels are actually not fully valid. The bottom panel is weighted GE after multiple imputation. So multiple imputation was used to make it monotone, and then I apply weighted estimating equations. Good. And then I have the observation level and the subject level, and you see once again that it makes a difference. I have pretty significant results with the observation level weights, which are the more efficient ones, and only one borderline significant result with the subject level weights, which are a bit more wasteful. Okay, that's what the output looks like. And then I would like to conclude not with a full overview of the sensitivity analysis techniques, but just a brief overview of what you can find in some earlier chapters, and I will spend a bit of time on one of the later chapters. So what I do in the selection model and local influence part is actually illustrate that if you do a naive analysis of missing not at random, you might be inclined to conclude, hey, the model that I fitted under MNAR is an improvement over MAR, so I have shown missing not at random. This part, and I leave it at that, is intended to say no, no, no. What often looks like evidence for missing not at random almost always has to do with other aspects in the data set. For example, in this mastitis example, it has to do with the fact, and I will go a little further down where you see this, some profiles are unusual, influential profiles. Two cows with a very high slope, and that's because they were sick the first year and should not have been in the data set, and they are completely drive the conclusion of missing not at random. But that's all I wanted to say about this part. Then I will go on to the second part. You can look at it in detail. It's not because I'm going over it that it's not important, but the models that we are fitting here under missing not at random are not easy to do with the standard software procedures or functions. So that's not something that I would expect in your assignment, of course. In the growth data set, we try to figure out what did Little and Rubin do. They removed, as you know, at the age of 10 years, 9 measurements. How did they do that? We analyzed the data, and actually I asked Don Rubin, and we came to the same conclusion. What they did is they removed boys under 22 at the first time, under 22 the first time, then they were removed. Under 20.75 the first time for girls, they were removed. In other words, the 9 measurements with the smallest value at the first time were removed the second time. Okay. With the interval of ignorance, again, we actually illustrate that it's a bit like with multiple imputation. When you have missing data, uncertainty comes from two things. First of all, a finite sample, that's always the case. But second, because you can never be certain about the predictive distribution. Yeah, you can work it out, and that's what we do the whole time under missing at random. But if you say maybe it's not missing at random, you can no longer identify it. So we then have to do something differently. Okay, so I think the case of the Slovenian plebiscite is a very important one to familiarize yourself with, to understand what we are talking about, but I will not look at it in detail right now, but rather go to the final part, which is some sensitivity analysis techniques that I can do with PROC-MI. And that's because that is something that I can do in practice. Okay, so for that we go to pattern mixture models. And pattern mixture models we apply to the Vorozol data set, which is a cancer clinical trial where two products are compared with each other. And in this study, in this data set, patients are followed up over time for their quality of life. Okay, the FLIC score, and the total functional living index in cancer score. Good. First thing we do is build a selection model, and this selection model is of a relatively simple nature. Now, because we look at change versus baseline, there are only interactions with time, because at baseline there is no change from baseline yet. It should be 0 at baseline. So that's why the fixed effect structure all has the time effects present. But of course, we are most interested in the interaction between time and treatment. It's a relatively simple mixed model with a random intercept and also some serial correlation. Okay, now if we look at the dropout model, and here we do something that is not so easy with standard software. Again, no need for you to do it, but just to understand what we do here. If we compare missing at random with missing not at random, it looks like we have a significant result. And that again may lead us to the naive conclusion, we have missing not at random. But wait a minute, if we look at missing not at random in the top line, we see that there are, of course, two outcomes. A standard missing at random dropout model would allow you to correct for covariates, for example, the baseline value and the previous value, for example. Missing not at random would not only use the previous value, but also the current value. And for that, we need some dedicated integration and stuff like that. Okay, but the key point is you have the previous and the current measurement indeed. So that allows you to look not only at one, the other, but also how they differ from each other. And hey, one has a negative coefficient, the other one has a positive coefficient. That usually means that there is a dependence on the evolution. And of course, we can extend the missing at random model in the same way by not only using the previous outcome, but also the outcome before that. In doing that, it's still missing at random because the previous and the one before are observed, but it allows us to look at the difference and the average. So what we conclude based on this model is that dropout is worse, increases with a poor baseline value, with a high level of the score, or a low level rather, of the score right now, and with a disfavorable evolution. So dropout increases with a low score at baseline, a low score now, and a negative trend. What else are you going to expect? So sometimes the evidence, so-called for missing not at random, is nothing else but an indication that we don't need a single value, but we need two values to get a good idea of how dropout actually works. Okay. Now, we switch to pattern mixture models, and here we have the average profiles in each one of the two groups, and they're like spidery. But if we build a model for it, we kind of see a more interpretable picture. What that picture says is, for each of the patterns, if you increase, you're fine, but the moment you reach a plateau and start to go down, that's usually the beginning of the end. Again, that's what we would expect, as long as patients are proving they stay in the study. But all the profiles, and it's even clearer in a more elaborate model, all the profiles actually, are going towards dropout once a disfavorable trend starts. We can build a pattern mixture model in many ways. We can build them such that there is still one single treatment parameter, but it's not uncommon in a pattern mixture model to have a treatment effect in every one of the patterns separately. In this case, there would be 13, and then you need to do a test on all those 13 parameters together. Or what you can also do is, with 13 treatment effects, average the treatment effects, for example, averaged by the sample size in every pattern, and look at the weighted treatment effect. Now, this is a sensitivity analysis of its own, because no matter how you do it, with the selection model from before and with various pattern mixture models, there is no treatment effect. So that is the common conclusion that we reach here. How to do that last thing, and that estimation with the delta method, is explained in some details here. But now, how do we fit the pattern mixture models? There are actually three major ways, and I leave it at that and then move to the things that we can do with SAS and conclude the session. I can build a simple model per pattern by making pattern a covariate. It's simple as that. I can use, so that's the second thing actually, I can use pattern as a covariate, or I can apply identifying restrictions. And I'll say a few things about identifying restrictions here this way. So let's now try and focus only on pattern 2 and build a model for the 3 outcomes in pattern 2. It's all nice and well. I do not have the third outcome. So what I need is the distribution of the third outcome given the first and the second. There is my predictive distribution again. Indeed, there is my predictive distribution again, which I used with multiple imputation. Indeed, which I used with multiple imputation. And that's why there is such a natural marriage between multiple imputation and pattern mixture model. But back to what I was trying to say, a predictive distribution for the third outcome given the first and the second, I can get from pattern 3, of course. So that's how I can identify that from the completers. Now, if in pattern 1, I first need a predictive distribution for the second measurement given the first, how am I going to do that? I now have 3 options: from pattern 2, from pattern 3, or from pattern 2 and 3 combined. And these are the 3 identifying restrictions from the previous slide. If I say from even in pattern 1, I go back to pattern 3, the completers, then I borrow information always from the completers. If I borrow from the closest pattern nearby, then I borrow from the neighbors. And if I do it from all those patterns on which the second measurement and the first are jointly available, we call that available case restrictions. If I do that in a certain weighted way, the available case restrictions are missing at random. Very important. One of the restrictions correspond to missing at random, which means other restrictions deviate from it and can be used as sensitivity analysis. There are some results here. In this case, usually the simple strategies, like using pattern as a covariate, or the first strategy, which was a simple model per pattern, may be easy to use, and they are, but they may lead to very unrealistic predictions, like you are going down as long as you are observed in terms of quality of life, but after dropout, your quality of life would tremendously increase. Nobody believes that. So the restrictions are actually better to work with. Okay. pattern mixture analysis of the ARMD trial with the restrictions, we can do those in SAS. ACMV is just the plain. DCMV and NCMV can be done in SAS. So what you can conclude is, well, the point estimates do change a little bit, but the conclusions at the end of the day, they vary, but not to the extent that something non-significant would become highly significant or vice versa. So the conclusion remains, we don't find anything. Okay, so we are now moving towards the final part that I wanted to cover, and that is we can do sensitivity analysis based on multiple imputation. What again is the tool of multiple imputation? The predictive distribution from which we draw. That predictive distribution is the distribution of y miss given y ops and the covariates as it follows under missing at random. So the only thing we need to do is change the predictive distribution in every way that you have in mind. You can say, okay, I take that missing at random predictive distribution and I play around with it a little bit. I draw from it, and every draw I add a certain amount, a shift. I shift upwards, I shift downwards. Or I inflate, say after dropout, the variance gets larger, so I change the variance a little bit. Or what you can also do is say after dropout, the predictive distribution will not come from everybody, it will come from the completers, from the placebo group only. Or you can use pattern mixture strategies. So here is an example. It's merely meant as an example. I do the same imputation as before with one important difference. I am going to apply the MNAR statement. So ProcMI has an MNAR statement that allows me to do precisely sensitivity analysis. So at week 12, I shift by 10 in the active group. At week 24, I shift by 15, and at week 52 by 20. Of course, we can now start to play with these numbers and say, why don't we start, rather than with 10, 15, and 20, gently with 1, 2, 4, for example. So you can play around and even find a point at which you need to apply a shift until the significance starts to change. And then you can see where that happens. If it's really far away, in a place where you don't consider it clinically relevant or biologically plausible, like you need a body mass index of 150 before it changes, forget about that. That's not going to happen. Excuse me. Then you can conclude for the stability. A subgroup adjustment, as I said. So here you do the adjustment only based on the predictive distribution from the placebo group. So in the placebo group, you correct based on the placebo group, bingo. But in the active group, you also generate from the predictive distribution from the placebo group. Now let's do NCMV. The thing is that NCMV doesn't work with non-monotone data. And that's what I said earlier. Here we can use ProcMI to first make the data from non-monotone monotone. Once that's done, I apply multiple imputation again under NCMV, so under missing not at random. Very important, if I need 10 imputations at the end of the day and I apply multiple imputation twice, you start with 10 immediately, and the second time you do a single imputation. Does it become single imputation? No, because you will singly impute every one of the 10 data sets that you already have, so it remains 10 and it's still multiple imputation, but not the other way around. So you start with the right number of imputations, and then in subsequent imputations you keep that number. Okay, so here are the two subsequent calls. So the input of the first one is number 13. The output is number 13A-3. The input of the second one is 13A-3, and then the output 13A-4. So 13 is general missingness, 13A-3 is monotone missingness, 13A-4 is fully imputed and completed. The first the logic is that intermittent missing values, usually are not suffering from a very difficult missing data mechanism. But dropout may well be. For one, people may die and therefore drop out, but that's not possible with intermittent missing values. And it allows us to do the second time an imputation based on the already monotone data set. And you see the first time I use MCMC impute is monotone. So that says, wait a minute, do not impute after dropout. That's what it says. And the second time I use the monotone statement. The first time the monotone option, the impute option actually in the MCMC statement. Now the monotone statement says, okay, the input data set are monotone. Of course, I just made them monotone. And I'm using NCMV. I can also use CCMV. I cannot use ACMV. And sometimes that's a question asked in an exam session. Why not ACMV? Because that's missing at random. So basic imputation is already ACMV. That's why you don't need to do it specifically. In the output, you get to see what it did, and this actually should be exactly what you put in the model. And then I get my sensitivity result, my simple sensitivity analysis, MAR, and then the shift, the using placebo group to impute, and then the NCMV. You see that the point estimates actually tend to change a little bit, as some people even say, hey, 41 and then minus 43. Oh boy, it swapped sign, true, but without changing the significance. Of course, I would need to go a little further to change the significance. Okay, and that brings me to the end of this part, and actually the end of the course. So what I wanted to repeat again, that's the slide that we saw in the middle as well, is under missing completely at random and simple, don't use those techniques. Go straight for your primary and your basic analysis. You go to direct likelihood, direct base, weighted estimating equations, but remember there are many downfalls, multiple imputation also, and then supplement it with the sensitivity analysis. The sensitivity part is relatively large, but local influence and the interval of ignorance, those chapters are there to give you a good sense of where does the sensitivity come from and where do I need to be careful in my interpretation. But the final part in the pattern mixture / MI sensitivity analysis, there we offer techniques that you can easily do in practice indeed. Okay, and on that note, I would like to thank you for your attention. Let's see. Between MI combined with GE, weighted GE and GLMM using direct likelihood. The weighted GE tends to basically, direct likelihood is something, of course, you apply with GLMM. That's what I would do. If I would use GLMM just as such, that's what I would use. With GE, I have to do something else. So there I would prefer MI GE. Would I do MI with GLMM? No, not if that were my only interest. But if I, like I did in the course, if I want to compare GE with GLMM, for example, to see what the difference are, as we discussed in the second part of the course, the marginal versus hierarchical inference. So if I want to do two different analyses, one of them non-likelihood like GE, then I would do multiple imputation and do all my analyses that I want to do, some likelihood, some non-likelihood, using multiple imputation indeed. But the reliable results, they come from using multiple imputation and or direct likelihood. Of course, we can always find pathological cases where one is not really performing very well, etc. But by and large, multiple imputation and direct likelihood, or sometimes also called ignorable likelihoods, are fairly robust techniques in that sense. Direct likelihood works under MAR, and that's an assumption that I cannot verify. So whatever my primary analysis is, direct likelihood, direct base, weighted GE, multiple imputation under MAR, that's my primary analysis. Ideally, I would then also do a sensitivity analysis in all of those cases indeed. All right, so no, not necessarily. I mean, you do not need to do multiple imputation. Sometimes people do also in the assignments multiple imputation as a sensitivity analysis to likelihood. Now, if you do basic multiple imputation under MAR and you do likelihood under direct likelihood, you should get more or less the same result. So that is not a sensitivity analysis in the way that we discussed. They're both basic methods from the middle category here in this. The only thing that it does is it gives you some confirmation that your programming in both cases, it's a numerical sensitivity analysis, but not a missing data mechanism sensitivity analysis, because if there would be a major difference between multiple imputation mixed model and direct likelihood mixed model, then usually something is wrong, something very pathological in your data set, or simply a programming error. So it's good for debugging and for numerical stability, but a sensitivity analysis really takes your basic technique under MAR and takes it into the missing not at random world with some of the techniques that I have seen here. All right, if there are more questions, feel free to ask them.
Hello?
Yes.
Okay.
Yeah.
Because I have a question. Just for example, after we compare the results from slide 747, then maybe we found something weird. Then we can just adjust the model covariance structure or the mean structure to see after adjustment, then there's some not improvement,
Yeah.
but yeah.
Not necessarily, because if you see, let's say, if you see a major difference between MAR and NCMV, say, like one is highly non-significant and the other one is highly significant, that doesn't point to a mistake that you have made. It might, but it may point to the fact that your conclusions are very sensitive to the missing data mechanism. And that's then a result you have to live with and say, hey, wait a minute, we have reasonable doubt that it's very hard to determine the actual treatment effect here. Because let's say if I have 90% missingness, very bad case. I have a data set and 90% of the measurements are missing. Be sure that your sensitivity analysis will go over the place. All that is saying is you have very little information and a lot of uncertainty, and you cannot make very reliable conclusions. And that's why we do sensitivity analysis. Here in this case, we seem to see that, yeah, we have fairly stable results. Nothing is happening. Even if you shake your missing at random analysis a little bit towards shift and placebo and NCMV, it pretty much remains the same.
I see. And another question is just about normally we impute only the response variable.
Yeah.
And if you are curious about what covariates that play some critical role, we can also impute the one of the covariates to see what.
It's a good point. Actually, something that I also say in the slides, and I want to repeat now, is a major advantage of multiple imputation is you can and actually should impute both the covariates and the outcome simultaneously. Because otherwise there is still a problem that many analyses will delete observations with incomplete covariates. And that's where direct likelihood breaks down. Because if there are missing covariates, it's not easy to use direct likelihood unless you start to model the covariates as well. We usually don't want to do that. We want to condition on our covariates. So multiple imputation can be used to impute covariates and outcomes simultaneously so that everything is complete. There are no holes in the data set that you're going to analyze, and then you can build a model that you had in mind in the first place. So do them together. That's the idea with missing covariates.
I see. Just because sometimes, for example, the value should be exactly positive, but after imputation of the covariate, some value become negative, then it's not realistic,
Yes.
I think. Then
Yeah,
what to
but
cope with?
there are solutions for that. So many multiple imputation software tools can set bounds. So you say, for example, greater than 0, then no negative values will be imputed. What I prefer to do is sometimes I use these bounds, but what I actually prefer to do is a transformation. So, for example, let's say I need to impute body mass index. Usually we would not do that. We would impute length and weight and then calculate body mass index. But okay, let's say body length. Body length should be positive. You use the logarithm of body length that you impute, and after imputation you exponentiate and everything is nicely positive. So by using transformations, you can make the imputation obey the range, be it positive or be it falling into an interval or something like that. So usually we can use transformations for that.
Ah, I see. Thank you. So
All
it's
right.
kind of we need to decide. We still have some domain knowledge for what kind of trick like transformation we need to
Yeah.
apply.
Yeah.
Okay, thank you.
And in the imputation task, indeed, you just specify, if you do MCMC or a general tool, you don't need to specify the regression equations. You just make certain that you include all the covariates and the outcomes that you are going to use in the final analysis. In the regression equations, you build them for every variable that is incomplete based on the information that you think will have an impact on those outcomes indeed. So that's a little bit of, let's say, that depends on that's a modeling exercise like any other model exercise. Like what we did in the example is say, okay, the macular degeneration example, the visual acuity depends on the previous values of visual acuity and on lesion and on treatment. Okay, that's you can say it may depend on other covariates as well if they are available. So it may even depend in the imputation task on more covariates than what you are going to use in the final analysis. So that's one of the other advantages. You can really make the imputation model fairly rich by adding what we call auxiliary variables that may lead to better predictions, even though you're not necessarily going to use those auxiliary variables in your final model. But whatever you use in your final model should be present in the imputation task. So the imputation task can use more, but not less than the analysis task.
Okay, thank you.
All right. So thank you for your attention and for the interesting discussion, which allowed me to clarify a few further and important things, because multiple imputation is used a lot indeed in practice, because it's a good technique with good properties, very widely general and applicable, and also we have the software to do it. So soon the assignment will be available, number 3. Sorry for that. I know you're still working on number 2. And regarding number 2, a timetable will be made available relatively soon for the 4th of December as well. Thank you very much and see you at the next occasion.